So this is from Tina Tsou. She wants to talk about AI and brain to computer, computer to brain, and this will be a fantastic session. We had seen the neural networks of the 50, she wants to do a flops and mega flops of a floating point. Let's see how she does it. Welcome. Any help?
Hello? So, hello everyone, and thank you for the opportunity to share this presentation about the race to neural class networks. I find this topic inspirational because it presents an explosion, exciting and interesting new technology, as well as a bright future for the NFIC represented here tonight. So let's get started by answering the question, what is the race all about? Well, the race to neural class network is about reaching a couple of destinations simultaneously, all around the world. My guess is hundreds of thousands of people are working to understand how the brain works. And at the same time, others are using that information to build information technologies that work like the brain. Both areas of research, learning about the brain and applying that research to IT, are places where you will find the very best engineers in the world. Neural networks are in some part a spin-off technology among many that are being driven by hyperscale cloud service providers. Development of these spin-off technologies require the best engineers in the world because they are all breaking new ground. And in the same way, the NASA spin-off technology has made a huge and lasting impact on mankind. Neural networks promise to have a profound effect on our planet. Now, let's look at our understanding of how the brain works. Starting an example of new class of tools needed to develop neural networks. It's not something you can order on Amazon.com for your lab. This is a helmet of sensors at the Martinos Center for Biomedical Imaging. Part of a brain scanner requiring almost as much power as a nuclear submarine. Antennas pick up these extremely hard to measure signals, which computers convert into brain maps. With tools like this, someday soon, complete maps of our brain signals will sit alongside maps of our DNA. With helmet sensors and other tools, we've learned there are about 100 billion neurons in each of our brains. And neurons are to the brain what servers are to our data centers, the basic building blocks of computing. Each neuron or server has about 10,000 network ports, which totals to somewhere between 100 trillion and 1 quadrillion connections in the brain. The network cabling of the brain is axons, or white matter, in the middle. The brain's many regions are connected by 100,000 miles of white matter's fiber, enough to circle the Earth 4 times. Images like this reveal the specific pathways underlying cognitive functions. The pink and orange bundles transmit signals critical for language. There's a lot of data in the brain to be accessed, and it has to be stored in order to be accessible. Using our crude mapping tools, and imaging techniques, we would need 450,000 terabytes of storage to store an image of a mouse brain, and 1.3 billion terabytes of storage to store a full image of a human brain. That storage needed for a human brain image is 3 times the amount of storage projected for our entire planet 2020, even with an explosion of data due to the Internet of Things. So, with all those neurons, cabling and storage, we must need megawatts of power, right? The answer is a big no. The amazing human brain packages all the computing infrastructure in only 77 cubic inches, which needs only 20 watts of power, about the same as a light bulb or a Nintendo Wii. This is what the packaging for 100 billion neurons, 100 trillion network connections, and 1 billion terabytes of storage looks like a close-up. The image on the left shows the cell body and transmitters of a mouse brain. At 10 microns, we can see the blue network cabling, a data center network engineer's nightmare. And at 3 microns, this incredible photo shows network connections between 2 of the 100 billion neurons. The neurons, or servers, in your brain are networked to take input, perform massive parallel processing across the regions of your brain, and provide output in the form of thoughts, speech, movement, or all of the above. The response time for each region is in milliseconds, similar to the user response time we expect from transaction-oriented enterprise applications like reservations systems. It makes me wonder if the expectation for millisecond performance is not a coincidence. Maybe acceptable lag time is matched with our own ability to process a transaction. This is my last slide on understanding the human brain. Now, let's look at what we are doing to build IT that works like the brain. At the root of the development of IT that works like a brain is building computing infrastructure where algorithms are learned. Like us, the infrastructure is born with learning and reward machinery. From that point on, future IT will take input, learn, and produce output on its own. As an engineer, I find this premium tremendously exciting. As a human, I find it a little scary. The architecture for IT that works like a brain is called neural networking. Although the word networking is in the name, the architecture is for a computer systems modeled on a human brain and nervous system. And the goal of neural network is self-directed information processing. The neural networking architecture comes to life in artificial intelligence, a subset of that called machine learning, and a subset of that called deep learning. AI refers to tasks that normally require human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. Machine learning replaces hand-coded software routines and specific instructions, with algorithms to parse data, learn from it, and then make a determination or prediction about something in the world. Take neural networks. make them huge, increase the layers and neurons, and then run massive amounts of data through the systems to train it. But not all huge environments are proper neural networks. Hyperscale environments are also massive environments with millions of servers and connections. That's why the industry came up with the term neural class networks. The picture on the left is a proper neural network with layers of deep learning computing working on 1 billion parameters. The picture on the right is the traffic growth at the neural class network at Facebook, which supports over 1 billion users. Now, let's look at how our compute and networking infrastructure is evolving to neural class. Let's start with the year 2000 and examine how many servers the neurons of neural class networks fit into the out of 100 servers in the background. The year 2000 was the last year before dual-core server processors were introduced. That means the IR was filled with 100 server and 100 cores. Not really neural class. Now, let's leap forward to 2018. This out includes almost 5,000 cores using 48-core ARM-based Qualcomm-centric CPUs. Given that a neuron has 10,000 networking ports, this environment is approaching neural class. In this slide, we see that GPU-based environments are where the industry has finally smashed through. A single NVIDIA DGX1 system is neural class with over 40,000 cores. A data center out that housed 100 cores in the year 2000 now may include over 4 million cores. This achievement also embodied the most urgent challenges facing network engineers today. In the past, networking was commonly thought of as local area networks and wide area networks that connected systems. Today, with so many cores inside a processor, we must think in terms of inter-working cores inside of a CPU, cores inside of a GPU, multiple processors inside a server, and multiple servers inside a data center or dispersed around the world. Of course, in every case, there is an insatiable appetite for higher bandwidth, lower latency, and infinite scalability. Next, I would like to share a fun video with you that illustrates how the availability of more cores used in distributed environment is transforming applications.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target, hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
And 10, 9, 8, 8, 7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
All right. The same neural class technology that was used to create Mona Lisa is enabling real-time recognition and language translation. Also, you can see the electronic nose has the same function as human beings' nose. The same neural class networking technology is enabling superhuman vision. Show Planet a photo, and it will tell you the location of the image. The same neural class networking technology enables AI to reduce the error rate for cancer diagnosis. And the same neural class networking technologies has taken Tesla to level 2 and Google self-driving cars to level 4 in the National Highway Traffic Safety Admission classifications. To support smart cities, including self-driving cars, in the 4G era, a relative few number of data centers were used to support traffic nationwide. In the 5G era, thousands of micro data centers will exist on the cell towers, and millions will blanket the planet. We need highly distributed data centers to provide the low latency for the real-time analytics we want in our smart cities. In this use case, edge computing solutions act as gateways. These edge solutions aggregate local data from the traffic signals, GPS devices, other vehicles, proximity sensors, and so on, and process this information locally to improve safety and navigation. On the upper left are the edge servers deployed in cellular base stations that host applications and cache content for local subscribers without having to send traffic through a congested backbone networks. The pinnacle of our achievement and the world's most powerful supercomputer a Sunway Tahat light. It features 10 million cores spread across 40,000 nodes to deliver 93 petaflops of processing power. If you're thinking about a Sunway for your home, you will need 15 MW of spare power and 2,250 square feet of actual floor space. Now, let's look at how this magnificent machine compares to the organic computing machines. In terms of processing power, at 93 petaflops, the world's fastest man-made computer has greater processing power than a mouse brain, but less than a single human brain, which requires more than 100 petaflops to simulate. However, if we continue at this trajectory, by 2050, we will engineer computers with the processing power of all human brains combined. In terms of packaging, we have a long way to go. If we were to configure a rack mount server, configured like a human brain, it would be only 2.3 inches deep, but have over 100 petaflops of processing power, 1.3 billion terabytes of storage, 10,000 network ports, and include 100,000 miles of cabling. One example of fantastic networking technologies is BCI. People with spinal cord injuries can't move because the brain and the body no longer communicate. Scientists are working to restore the motion with a mechanical skeleton controlled by the wearer's thoughts. It's a daunting challenge. Hundreds of sensors must be implanted in the brain through a brain-computer interface to send commands to the exoskeleton. Signals must also travel in reverse, from touch sensors telling the brain where the body is in space. BCI is well on its way. Watch this video to see for yourself.
So this is the basis of the device that we've created, not only recording from one cell, but taking the pattern of many, many neurons and trying to relate what the person is thinking about to what something in the real world will do. And this is the setup that we have. The person has this electrode array implanted in their arm area motor cortex. We have now, in this rather crude, primitive version, because it's just an early stage version, they have a plug in their head. The electronics are connected by a cable that amplifies those little tiny signals, takes them through a computer, and the computer basically counts up and measures those spikes and tries to figure out, well, that means up, or that means open, or that means close. And what I'm going to do is show you some videos that show what the patients have been able to do. Of course, we were very excited, and we asked Matt, to do a whole bunch of things. Here he's going to draw a circle, and then he's going to tell us what it's like to be able to control something. So he's controlling that cursor with his thoughts. And this is actually the world's first art, I think, we're neurally drawn circle.
Oh man, I can't put it into words. It just, I used my brain. I just thought it. I said cursor go up to the top right, and it did. And now I got control of it all over the screen. It's wild.
He hadn't moved anything in a long time, so we were able to get this prosthetic hand, and it doesn't really do anything. It's just a motorized hand that can open and close. So we ran a brain command into it and told him, tell us what you're doing, and imagine opening and closing that hand. And you're going to hear his reaction to the first time he's moved something in a couple of years, because remember, he's completely paralyzed, and you'll listen to his strong reaction.
Oh, holy shit.
So just if you missed that,
So I hope you enjoyed the video and opened your mind to incredible possibilities. Beyond the BCI, like a brain-to-brain interface, which gives new meaning to the phrase B2B. As you can see in this infographic, work is already underway. It won't be long Before we will be able to silently communicate with each other using wireless connections between the hardware attached to our brains. However, even the incredible brain-to-brain interface is just another bump on the road for race to neural class networks. The ambitious Avatar project is hoping to use the BCI to make a robotic copy of human by 2020. After that, they would transplant a brain at the end of a human life by 2025, create an avatar with an artificial brain by 2035, and deploy a hologram-like avatar by 2045. If their predictions come true, this is what may happen. Our meetings that look like this today. They look like this with avatar speakers with artificial brains from real people who walked these halls many years in the past. This wraps up my presentation about neural class networks. It was fun for me, and I hope you had fun too. Thank you very much.
So we are into neural class of computers, moving from the hyper-converged infrastructure and computing. Thanks to Tina. You have any questions? Please go ahead. Yeah, Kevin looks interested. Yeah, go ahead.
So both Intel and ARM are hardware companies. I was wondering if you're doing anything on the hardware front to get the density of computing down, like moving to asynchronous methodologies and die stacking.
Yeah, please wait for on V9. which will be launched first half of 2009.
Any other questions? So I would call right now Hilka, come in, and your friend is here. Tina, you need to present her the certificate.